Hello everyone and welcome back. So remember what we were trying to do last time. If we have the space of continuous one periodic functions, and a little bit of omission here, it's implicit that these functions here have to be bounded. So I should have specified explicitly that this norm here has to be finite. About that. Anyway, so if we have the space of continuous bounded one periodic functions, and we have this this countable subset of 0 to 1 prescribed, then we claim that the set of all of these continuous functions, bounded continuous one periodic functions, where the Fourier series diverges for every single point in this prescribed countable subset of 0 to 1 is dense in this space here. And again, this is fairly remarkable. We're not just proving that there exists a bounded continuous periodic function whose Fourier series diverges at some point. We're not just proving that there exists such an F where the Fourier series diverges at every single point in this prescribed countable subset. We're actually proving that the set of all such continuous function, bounded continuous one periodic functions where the Fourier series diverges at every one of these prescribed points is dense in the space of all bounded one periodic continuous functions. Okay. And last time we went through this very basic, easy lemma that we're going to use in a very concrete manner in a moment. And I had a little issue with my digital pen last time, and what I meant to write didn't come out too well was that this here is bigger than 4 little m over epsilon, which it was, we picked x prime and I prime in such a way. So anyway, all right, so yeah, now let's put this abstract machinery to good use. So as typical in such applications of this abstract functional analysis, the studying Fourier series and Fourier transform, we have a natural sequence of bounded linear maps. In particular, let's just say Tn x for fixed x is just the partial Fourier series at x. Okay, so let's check that this is a bounded linear map. All right, there's really nothing to this. Just take the definition or the formula we have for the partial Fourier sum. It's just 0 to 1 f of x plus t sine pi 2n plus 1t over sine pi t. Smash in absolute values. Well, you can trivially pull out the norm of f, and you can check very easily that this function here in absolute value has a maximum of 2n plus 1. Okay, so this is because we exactly get the norm of f here. By definition, the operator norm for this bounded linear map is less than or equal to 2n plus 1. Okay. So I claim now that this actually, the supremum over all n is of these operator norms is infinite. And I claim that this is going to finish up the proof of what we originally wanted to do in these 2 videos. Why? Well, by our little lemma, this means that Rx is the countable intersection of open dead subsets of the space of continuous periodic functions. And remember that by definition, this is going to be the absolute value of partial Fourier series. Okay. Now let's apply this result. This is true for each x. Let's apply this to each xj in my prescribed countable subset of 0 to 1. So we get that we can write each rxj as a countable intersection of open, dense subsets of the space of continuous bounded periodic functions. So if we take the intersection of all these rj's, we still get the countable intersection of open, dense subspaces, and hence, by the Bayer category theorem, which is kind of our, you can maybe want to think this is our very fancy, expensive tool, the Bayer category theorem. And to apply this tool, we just have to put in hard work. Okay, by this very fancy, schmancy tool, this intersection here is dense. Okay, let's unravel exactly what this tells us. It actually tells us a little more than what we originally sought out to prove. Why? Well, let's look at this set D, where the Fourier series diverges for all x in this prescribed set. Okay, well, this is obviously larger than the set of all f where the partial Fourier sum blows up in absolute value at each of these xj's. Certainly, if it blows up, it can't converge. If the partial Fourier sum blows up, the Fourier series can't converge. You can't have a convergent sequence of complex numbers that blows up in absolute value. Okay, so this is trivial. Okay, well, this is our xj. Remember, I just said before that Tnx is Snf of x. Our xj is exactly this here, instead of x is xj. Okay. So the intersection of the rxj's is exactly this intersection here, because this equals rxj. And again, the fancy tool, Bayer category theorem, then says this is dense in the space of bounded continuous periodic functions. All right, so our task is now to prove this here. This is what we have to prove. And it's not hard, but there's no fancy, easy, slick functional analysis that will prove this. We just have to slog through some estimates, get our hands a little dirty, and check that this is true. And again, this is not hard, but this is work. And this is very typical of, applying functional analysis to the study of the Fourier series, the Fourier transform. We reduce the problem to an estimate that just requires work to do. And by that, I mean we use functional analysis to reduce the problem to just something that requires us getting our hands dirty. Okay, so let's begin doing this. So it's done in 3 steps. Each step is fairly straightforward. One of the steps is quite a pain in the ass, to be honest, but I'm going to slog through it in full detail, just because it's good to see it in full detail. So the first step is very straightforward. And the first step is taking this integral here. This will be the Dirichlet kernel with absolute values smashed inside, and proving that as n goes to infinity, this goes also to infinity. this integral goes to infinity as n goes to infinity. And this is not too hard. It's not a terribly subtle estimate here. Okay, so we all should remember that sine pi t, sine x over x is always less than or equal to 1. Sorry. Here it's pi t. Okay, so right, so in other words, we have sine pi t is less than or equal to modulus pi t. So because we have it in the denominator, we have it downstairs, it goes the opposite way. All right, so we just do an easy u sub. U is 2n plus 1t. This becomes the integral from 0 to 2n plus 1 of the following. Do the u sub, and you'll see that the 2n plus 1 cancel out. Okay, so we only care really about 0 to n. That's enough. And we break this up into k to k plus 1 for k is 0 to n minus 1. So we have pi u on this interval, and this should be du, if that matters. But pi u is bigger, or sorry, pi u is less than or equal to k plus 1. So it's in the bottom, so it goes in reverse. Pull out the pi in the k plus 1. And so here you can, it's a trivial, trivial calc 1 valuation that this is going to equal to 2. Really, because sine pi u is positive on each of these intervals, because of the absolute value. Well, sorry, you do want absolute value to get that each one of these integrals is trivially 2. Okay, so this becomes k equals 0 to n, 2 over pi, 1 over k plus 1. And obviously, when n goes to infinity, it's the harmonic series. This is, this goes to infinity. Okay, and actually, if you work a little harder, tiny bit harder, you'll get that just like the harmonic series. This integral here is of the order of natural log 2n plus 1 as n goes to infinity. Which makes sense. I mean, this is, remember the harmonic, I don't know if you've ever seen this. If not, it's not a big deal, but it's not hard to prove that the sum here is of the order natural log n plus 1. And we threw out even the terms n to 2n plus 1. We don't care. We just want to show that this goes to infinity as n goes to infinity, and this is enough to do that. Anyway, so that's we're done with the easy step 1. Okay, so let's look at step 2, which is assume I can cook up a sequence of continuous bounded periodic functions that have norm 1, where in the limit, this is going to converge to the absolute value of the Dirichlet kernel pointwise, as long as we're away from the zeros of the Dirichlet kernel. Okay? Now you might say to yourself, no, this is incorrect, because what about k equals 0, and what about k equals 2n plus 1? If you plug, well, that's, if you plug in t equals 0 here, it's really a removable singularity. It's 2n plus 1. Same thing if you plug in t equals 1. And it's a removable singularity, so, so there's really no issue there. Okay, so if we can do this, then we are done. That's the claim in step 2. Why? Well, this operator norm is trivially big or equal to this limit here, because we're just looking at Fj, and Fj here has has norm 1. Okay? So really, without knowing this limit exists, we should say it's the lim sup. But we do know this limit exists. Because, well, this limit here, sorry about that. Had my digital pen upside down. So, well, this limit here is just this absolute value. Okay. And the Fj times this here is going, well, first of all, for fixed n, as I mentioned, this is bounded by 2n plus 1. Again, for fixed n. Okay. So since this has norm 1, we trivially can use dominate convergence theorem, shoot in the absolute value, the limit, throw in the limit inside the integral. And because this whole thing pointwise converges to absolute value of the Dirichlet kernel almost everywhere, except for these points here, this finite set of points, well, we know, or we had from last time, that this is bigger or equal to 2n plus 1. Okay, so that'll trivially prove exactly what we need to prove, that the supremum here of these operator norms for each fixed x is infinite. Okay, and in particular, it's bigger or equal to 2n plus 1. And as doing a little bit more work, you can prove that as n goes to infinity, it behaves asymptotically like ln of 2n, sorry, this was, that was incorrect. It's not bigger or equal to 2n plus 1. We had that it was bigger or equal to, sorry about that. What was it? 2 over pi, 2 over pi. Bigger or equal to 2 over pi. The sum here, k equals 0 to n minus 1, 1 over k plus 1. Okay. Sorry about that. Right. And this here behaves asymptotically like ln of ln of n, and as I mentioned, you can, because we cut off really half of the sum, if you work a little harder, you can actually, prove from this here that this operator norm is going to behave as n goes to infinity like ln of 2n plus 1. But we don't, all we care is that this is infinite, and this certainly, because the harmonics series is divergent, it's infinite, certainly this proves that as n goes to infinity, this is going to be equal to infinity, so supremum is equal to infinity. Sorry. Long day. Okay, so step 3 is cooking up these functions here. So the idea is pretty straightforward. We basically want to look at the sign of the Dirichlet kernel. Okay, and what's the sign? Remember, the sign is positive when what's here is positive. Sorry, it's 1 when this is positive. So you look at the sign, whether it's positive or negative. If what I just circled is positive, this whole thing spits out plus 1. If what I circle is negative, this whole thing spits out minus 1. And it's not really defined. You can define it as 0. What I just circled is 0, but really for our purposes, we don't care what it is. When what I just circled is 0. And the reason is because this whole thing here, goes from positive to negative many times. In fact, as we'll see, it goes from positive to negative 2n minus 1 times on 0 to 1. And so this function here has a jump at these points where this whole thing goes to 0, so it's not continuous, and that's really not good. That's problematic. So let me just illustrate an example here. So let's look at, and I should mention, as long as, take any x not equal to 0, sine SGN of x is x over absolute value of x. That's fairly trivial. All right, so let's look at, let's do n equals 7. So 2n plus 1 is 15. So sine 15 pi x, sorry about that, over sine pi x. Well, we don't really want to look at that. We want to look at this over its absolute value. Okay, so just copy this. Okay, so let me move this up a bit. That, so I'll go back in a second. Actually, sorry, there we go. Okay, so, right, so here, as I mentioned, this whole thing here in the numerator has zeros. X is 1 over 14, 1 over 13. Sorry, not that, that's incorrect. It has zeros at x is 1 over 15, 2 over 15, 3 over 15, 4 over 15, 5 over 15, et cetera, all the way up to x is 14 over 15. When x is 0 and 1, it's actually going to be, it's going to be 0. Sorry, it's going to be 15. So, okay, so you see that exactly going on here. This numerator is positive until we hit 1 over 15, and then it has a 0, and then it becomes negative. And from 1 over 15 to 2 over 15, it's negative, then it becomes positive. So there's a jump here, 2 over 15 to 3 over 15, which is exactly 1/5, which is 0.2, which you can see here is 0.2. It's going to be positive, 3 over 15 to 4 over 15, negative. And we just keep having these jumps. So we have these 14 jumps here. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So what we're going to do is not so subtle here. Okay. Dump this in. Oops, sorry about that. I meant to do print screen. Copy. Okay, so what are we going to do here? So actually, I'm going to have to make this a little bit smaller. That should be good enough. So bear with me for a second. Sorry about that. Okay, so I can probably make this a little bigger. I think I'll leave it here. Okay, so right, so we're gonna have to modify this a little bit. So the basic idea is going to be as follows. We're going to take each of these problematic points here, basically cut off a tiny bit to the left, cut off a tiny bit to the right, and then connect with a line. Okay. So not a terribly subtle idea here. Whoops, sorry about that. Right, so we connect by a line. Do the same thing here, and just basically repeat. So I'll explicitly write things down in a second. Cut off a little bit more here. Right. And so that's where the J's are going to come from. We're basically going to let the amount we cut off get smaller and smaller and smaller, so that except at these problematic points, we're going to have convergence to the sine function, SDN of the Dirichlet. So we do exactly this here. Oops. Sorry about that. Go up to here. And yeah, just continue on. I'll do one more here. Cut off a little bit here. Cut off a little bit here. And connect the dots with the line. A little bigger. Okay, so yeah, I mean, you get the point here. We just keep going here until we genuinely get a continuous function. Okay. So maybe I'll just not erase, but just write these lines here just in case there's any confusion whatsoever. Right. So I should maybe emphasize that these are going to, actually have genuine slopes. They're not vertical lines. Not a function, of course, but anyway. Okay. Right. So now we're done. Okay. So, right. Let's do everything explicitly. So, right. Define fj tilde to be the sine function for t away from these problematic points. And I quantify that by saying we're 1 over j away from these problematic points for j nice and large with respect to n. We can trivially do that without loss of generality because for fixed n, we're letting j go to infinity. I'll make this a little bigger. Down a bit. Okay, so explicitly, we're breaking up 0, 1 into all these, we're going to let t be in these union of these intervals ij. So I wrote down what's going on here. It's a mess, but it's really not too bad, really. Make this a little smaller, try to fit this all in one page. I'm gonna make this a little smaller. Sorry about that. 100%. Perfect. Okay, so let's look at this interval first here. 1 over 2n plus 1 minus 1 over j. 0 to that. Okay, so these are our problematic points. Again, when n is 7 in our example, it was 1 over 15, 2 over 15, 3 over 15, et cetera, et cetera. Okay. So this interval here is going to be exactly right here. Okay. We're away from this problem here. Okay. Now this next one here for k equals 1 is going to be 1 over j plus 1 over 2n plus 1 to 2 over 2n plus 1 minus 1 over j. So we're just going from here 2 here, right? So this one here, sorry, didn't want to do that. Sorry about that. So this is 1 over j plus 1 over 2n plus 1, which is exactly what I have here when k equals 1. And the other endpoint is 2n plus 1 minus 1 over j, which is what I exactly have here when k equals 1. So we keep going until we hit finally the last endpoint, which I'm scribbling in here. Because again, we're away from our last kind of bad problematic point. Right, and this is just 1 over j plus 2n right here. Right? And I couldn't fit it, but you know, this this here would be 3 over 2n plus 1. Okay, right. So right. So in all these points that I'm scribbling red, also this would be a place to scribble red too. You can check that. So for all these points where we're scribbling red, corresponds to these red 1s and minus 1s. So all we're going to do is just exactly what we're doing here. We're going to connect the 1s and minus 1s on these little intervals by line segments. So on these bad intervals, just connect the line segments, the left line segment and the right line segment. So let's just do k equals 1. So this is 1 over 2 n plus 1 minus 1 over j, 1 over 2n plus 1 plus 1 over j. Next, this is 2 over 2n plus 1 minus 1 over j, 2 over 2n plus 1 plus 1 over j. So et cetera, et cetera. So we're just doing exactly what we're doing. We're connecting these 1s and minus 1s by line segments to get a nice continuous function on 0 to 1. All right. Okay. Right. All right. So certainly for t, not one of these problematic points, we're eventually going to fix such a t. We're eventually going to be in the in the red here. So we're eventually going to be certainly in one of these intervals as j goes to infinity, because we're explicitly avoiding. We're explicitly, getting closer and closer and closer to, from both directions, these problematic points. So point-wise, we have convergence to the sign. Okay, so finally we set fj of t to be f tilde j of x minus t. So just literally plug in x minus t for t. We get f tilde j of t. And so that finishes up the proof. Because this limit here is going to be, as long as we're away from these problematic 2n minus 1 points, it's going to be the sine of the Dirichlet kernel times the Dirichlet kernel. And the sine of anything times anything is its absolute value. That's trivial, absolutely trivial. And so that proves it. So I hope everything I did was very explicitly clear here. These constructions are just often messy if you just explicitly do them, but there's no way around it. And certainly, online graphers, when you have very explicit functions like we do, are very, very useful. And if this isn't even convincing, do something like n is, I don't know, 10, so that 2n plus 1 is 21. Now, these don't match, you get a really weird function, but yeah, and here you can again count. You have 19 of these jumps here that you have to, handle by this, cut off tiny little pieces near our problematic jumps and connect via these yellow line segments. Anyway, okay, so yeah, like I said, I really find these arguments beautiful. Using abstract functional analysis to prove fairly concrete results about Fourier series. If this looks like some magic trick, let this sink in for a little bit. Okay, so what we're going to do next is talk about how to prove convergence of Fourier series for functions that have jumps, like I drew in the previous video. And after that, we're going to dive into the L2 theory of Fourier series, which is very beautiful, very elegant, and frankly, very easy. And really, we're going to drive home the notion that life is often pretty good when you are working in a Hilbert space. You've probably seen that already. In functional analysis, Hilbert spaces are really wonderful. When it comes to Fourier series, Hilbert spaces are really, really wonderful. Orthogonality makes things so simple compared to the LP theory of Fourier series, when p is not equal to 2. So in comparison, we'll spend 2 or 3 videos on the L2 theory of Fourier series and basically spend the rest of the semester on the LP theory of Fourier series. Anyway, I've rambled enough for this video. Hopefully this was clear. Not ask me questions, put a comment on my video on YouTube, whatever. All right, so long. Take care. See everyone in the near future. Stay safe. New videos will come probably next week.